think we're ready. We're going to do a little more frames and machines today. There's one problem somebody asked to work through, and it's a good one to work through because it looks relatively simple. It's got two parts, but it's got a little bit of issues that we have to figure out how to work with. It is probably not representative of a test question. It's close. It's probably, if it was on a test, it'd certainly be one of the harder problems, although it looks really simple. But there's a decent amount of time you have to spend to solve it. So it's probably not quite representative of a test question, but it's close. It's like a little beyond a hard test question. But we're going to work that one. And then we're going to answer any questions that might pop up. And if there's no other requests for ones to try and work through, then we're going to talk about beams. Remember I said that frames and machines are not like trusses, even though they might look the same. Trusses have every piece in every member of the truss is a two-force member because of all of the assumptions that we made with loads only occurring at joints, no forces applied directly to members, no external forces anyway. We ignore the member weight, all those kind of things led to every member, every piece of a truss being a two-force member. But for a frame or a machine, that's not true. So for a frame or a machine, then we've got the issue that there is at least one piece, and probably more than one, but at least one piece of it that is not a two-force member, and that piece is going to be a beam. And so that the presence of that one piece meant that we couldn't do things like method of joints or method of sections, so we have to do this other process where we look at each piece of the frame individually. There can be two force members in a frame or a machine, but it could be that all of the pieces are beams. So we'll look at beams as a separate thing later today after we do our frames and machines. So the problem I was going to work through is this one right here. This is homework. This is from the web work. Homework 9, problem 4. So it looks pretty straightforward. There are two pieces and some cable and a pulley. The pulley's frictionless, that kind of thing. Only one force applied to it. But when you get to solving this one, it leads you down a bunch of paths where you don't have enough information. So this one would be a good one to work because it'll be a good one to work. One thing on this one, notice this italic here. The distance AG, so between these two pins, is deliberately not provided. If that one distance was provided, this problem becomes much simpler. Like it's almost a one-step, maybe two equation problem to solve it. But since that's not there, that one dimension's not there, that means that there's some summation of moments we can't do because we don't know the moment arm. And so it creates a much bigger problem. So I'm going to copy this guy and we will solve it. It says it's a difficulty 4 out of 5, so that is one of the harder ones. It's not a impossible one, but it does take a little bit of things. It's got some new things. There's a slot here that we haven't looked at, I don't think. I think we might have looked at a slider before, but we haven't looked at a slot. It also has two pins, so G and A are both pins. Normally, in statics, when we're dealing with statics and strength of materials from a statically equilibrium point of view, then two pins is like this key that there's something different because two pins create 4 external reactions, and we only have 3 equilibrium equations. So that means there's something going on that we're going to have to figure out, because if there are 4 reactions and 3 equations to solve those reactions, that means we can't solve all of the external reactions first. And so anytime in this course anyway, when you see a fixture of any sort, or frame, machine, truss, whatever it is, that has 2 pins, not a pin and a roller or a fixed support or something like that, then that's a kind of a visual clue that there's something that you've got to think through. All right, so I copied it. Let's paste it over here in our screen. Let me get the screen visible. There we go. There it is. let's just think through a little bit of stuff first. So this is one where if we went to solve the external reactions, AX, AY, GX, and GY, if we went to solve those, first of all, there's 4 of them. We can't solve all 4 of them for sure because we only have 3 equations. There are no 2-force members other than like the cable, the little rope that's going around the pulley. It's a 2-force member, but there's no 2-force members of the frame, so that's not going to help us. I don't know the distance between A and G, so even if I wanted to do summation of moments about A, I couldn't do it because I don't know how far away G is. And there's not enough geometry here to figure that out. You know, you might look at it and say, oh, well, I've got the slope of that line, that cable, and I've got H and C, but there's just not enough information to figure out from this diagram how far away A and G are. Even when we're done with it, we won't be able to figure that out. So that's not an option. So what that's telling me is that, all right, sometimes with frames and machines, you can't start by solving the external reactions. So you go right into the step, like I think maybe the 3rd step I wrote down. The first one is draw the free body diagram. Second one is look for 2-force members. This one doesn't have any. 3rd step, I guess, would be find the external reactions. So we have to skip that one because we can't find them. So the next step is look at individual pieces. So we've got piece ABC and piece CDEG. So we're going to look at those individual pieces. So let's draw those free body diagrams and see if that leads us anywhere. Hopefully it will, because we have to solve the problem. So we know it's going to do something. So this will be ABC. A's here, B's here, C's up here. At A, I've got a pin, and at pins I have 2 reactions, horizontal and vertical. They don't have to be horizontal and vertical, they just need to be orthogonal right angles to each other. There's no reason for me to do anything other than horizontal and vertical, so that's what I'm going to do. At B, I've got the little roller. Did they even say what it is? Pulley, something. It's a wheel of some kind at B. This is one of the good places to go in and do the thing I talked about last time, where you can, if it's a frictionless, which actually this doesn't say it's frictionless, but let's look and see if there's any notes here. Actually doesn't say anything about it being frictionless, but we haven't talked about anything other than frictionless, so we're going to assume that that pulley at B is frictionless. Maybe I'm just missing it and not seeing it, but we're going to assume that that's true. So when that's true, I can completely remove the wheel, the pulley, the sheave. I can completely take that out and put the tension in the rope around it right at the pin B. So that's what I'm going to do. I'm just going to label it T for tension in the rope, and do another one here because the rope's coming off from the horizontal direction also. I don't have the angle, but I have this deal where I've got A over B. For me, A is 5, B is 6. The hypotenuse here is 5 squared plus 6 squared. Take the square root of that. We need a calculator to do that. Let's see, 5 squared. Where's my squared button? There it is. 6 squared. Add those together. Take the square root of that. 7.81. So the hypotenuse will be 7.81. So that's what I'll do with that. I don't know any of these things. I don't know AX. I don't know AY. I don't know T. I do know that I'm assuming the pulley is frictionless. So I'm assuming that the tension on one side of the pulley is the same as the tension in the rope on the other side. So these both are T. I don't have to do T1 and T2. So they're the same value. I just don't know what they are. I have to be careful up here at C. So C is some kind of little wheel that's in a slot. So let me draw a bigger version of that. I'm thinking maybe even bigger than that. Hold on. So there's the little slot that, some kind of little thing like this. inside there's some kind of wheel. We'll do this as our wheel. And it's able to move in this direction inside that slot. So it can go up and down in our picture here. It cannot move this direction because it's constrained by the slot that it's in. So that constraint is the force on the wheel. And it's not on both sides. You know, I mean, I guess if I tried pushing it one way, it would resist. If I tried pushing it the other way, it would resist. But it can't resist both of them at the same time. So there's gonna be a reaction here in one of these directions. I'm gonna say, looking at our picture here, F, the external force, is pushing on the other part, which is causing the roller to push on the inside surface. So this piece is pushing back this way. Now, does that actually matter? I'm going to call it the F at C, so the force at C. It doesn't actually matter if I've got this direction right or not. If I get it wrong, then I'll calculate, and FC will turn out to be a negative number, and that's fine. So I don't actually need to know if this goes left or right. I just need to know it does one of those things. And I know it's horizontal. Well, I'm assuming it's horizontal because I'm assuming the little slot in part ABC is vertical. It doesn't actually say that, but it doesn't tell me any reason not to assume that. So I'm assuming that. And then I'm going to assume that the reaction inside the slot is frictionless. So the only reaction is perpendicular to the slot. So it's kind of like a roller. It basically is a roller. It's just inside a slot instead of rolling on the ground. So this is what I pick. Let's erase this thing so that we can draw our other one next to it. So I don't know anything about this. I know that I have 1, 2, 3, 4 variables, but I don't have anything that I know. I could put some dimensions on there, I guess. Let's do that. So it does tell me from A to C. So this dimension is H. H for me is 4.9 feet. So let's put it all in inches. 58.8 inches. And it tells me, well, it doesn't tell me directly, but I can figure out this dimension from A to B. A to the bottom of B, where the cable comes off, is dimension C, so that's 5 inches. And then it tells me that the diameter of this pulley is 11 inches. So that means the radius, this distance, is 1/2 of the diameter D. So my diameter 11, divide that by 2, 5.5, add that to C, which is another 5, is 10.5. So I do have this set of units, but that's all I have. So I can write the equations, summation of forces in X and in Y and a moment equation. I can write the equations, but I can't actually do anything other than that. So let's draw the other piece. So I'm going to draw it over here at the side, kind of in the same scale, just moved over. All right, so there's a pin at G, just like there was at A. Let's put our little pin. So there's going to be one at G, there's one at E, there's one at D, and one at C. So G, it's just a pin, so it's going to have GX and GY reactions. E is the tension in the cable, so it's just going to do that. D is also the tension at the cable. It's going to do this, and it's going to have that same 5, 6, 7.81 triangle, just telling me the slope. C, now C I've already drawn. On the piece I drew first, I drew FC going to the left. So on this piece, this is the reaction to that, or the one I drew first is the reaction to this one, whichever way you want to think about it. The main important thing is that on this one, I draw FC going the opposite direction because they have to be the same magnitude and opposite directions for them to be. This is Newton's, is that the third law? Equal and opposite reaction directions and magnitudes and all that kind of same magnitude, opposite directions for reactions. Also, F, the external force, is applied to this piece. So if you look over at my picture, F is pushing on this piece, not at C, but like right next to C. So it's pushing right here. That's the one thing I know. In my description down here, it says that's 160 pounds. So like that. So at least this one, I have one known thing. I also have some dimensions. I can put this dimension on here. Let's move that over, actually. Let's move it over a little bit. This was the same 58.8 that it was on the other piece. And then this dimension is given on the diagram as C, which is 5 inches. And that's the set of dimensions I have. I don't like GX being right there. There we go. All right. So I've got that. I do know one thing, but I've got 1 FC, 2 T, 3 GX, 4 GY. I have 4 unknowns on this, 3 equations. So that's not going to work. The first piece, I didn't even know anything, but I have 4 unknowns in 3 equations. But if I take these together, so between the 2 of these free body diagrams, I can write 6 equilibrium equations. I can write XY and moment for one piece, XY and moment for the other piece. So I have 6 equations. And between these 2 diagrams, I have FC is 1. There's 4 different T's, but they're all T's, so that's 2. Then AX, AY, GX, and GY, I have 6 unknowns. So I have 6 unknowns between the 2 of these diagrams, 6 equations. I should be able to solve it simultaneously, assuming I can write the equations and actually solve those equations simultaneously. I'm going to do it in MathCAD, but there's pretty simple equations, and I think you could probably do a substitution method without having to do, some kind of matrices or simultaneous equation solve or something like that. But we actually are going to use a solve block in MathCAD to set them up. But first, let's write the equations that we have. So let's just call this one part 1, and this one part 2, and let's see. I'm trying to figure out where I want to write these things. I think what I want to do. Oh, not that. I think what I want to do is copy these guys. Maybe I'll just copy them and paste them down here like that. All right, so actually let's do it this way now that I think about it. Let's put this one down here, and let's write the equations off to the side of the diagram. So this one, let's write summation of forces in x equals 0 for part 1 here. So I've got negative FC plus the x component of the angled tension. So that's T. I'm not going to solve the angles and do the cosine sine stuff. I'm just going to use the definition of what I need. So T times 6 over 7.81 to get the x component of it, plus T, this is the one that's horizontal, plus AX equals 0. So that's one equation. Let's do Y. I've got T times the Y component, so 5 over 7.81, plus AY equals 0. And then let's do a moment equation. Let's do the moment about point B. I'm choosing point B because it will eliminate the most unknowns and it will make the equation easier. So that will give me, I did clockwise positive, so minus FC times, I didn't write that dimension down. That'll be this dimension, 58.8 minus 10.5 is 48.3. There we go. So FC times 48.3. I will leave the units off of all of this. I've converted everything to inches, and the only other unit is going to be pounds. So I'm just going to leave them off for now, just to save some writing room. I don't like leaving the units off in general, but just to make it cleaner on the page, I'm going to leave them off. They're all converted into inches and pounds, though. T, the other T, and AY, their lines of actions all go through point B and do not create moments about point B. So we're left with minus AX, minus because it's going counterclockwise, and I said clockwise was positive, times 10.5. Okay. That's it. Now you might think, well, you could just write a whole bunch of moment equations. You could write a moment about B, a moment about C, a moment about A, make up some other point, write a moment about there, and you're right, you can do that, but they're redundant. They're not new equations. So you can't just write a whole bunch of moment equations and solve them simultaneously somehow. They are all redundant, so they don't give you new information. So you can't do that. But so there's 3 of our equations, but there are 4 unknowns in here. So I'm going to have to write the next set of equations. So let's see, what did I do? I did x, y, and moment. So summation of forces in the x direction for this piece. I've got 160 pounds. I'll put the pounds on there. Plus FC minus the x component of this angled tension. So minus T times 6 over 7.81 minus another T plus GX equals 0. So I think that's all correct. Yeah, I think that looks right. Summation of forces in Y. We've got the minus T times 5 over 7.81. That's the Y component of the angled tension in the cable. Plus GY equals 0. And then we've got a moment equation. This one I'm going to... Oh, I didn't write my letters down. These are C, D, E, and G, I think. So C, D, E, and this one was G. I'm going to do summation of moments. I'm going to do D, I think. Same reason as I chose B on the last one. If I do D here, then the 160, FC, the angled T, and GY all do not create moments about D. So that'll make my equation relatively simple. So it'll just end up being GX going around counterclockwise, so minus GX times the moment arm of 58.8 inches plus T times its moment arm of, I didn't write that down, 53.8 inches. Equals 0. All right. Now I have 6 equations, these 6 right here. 6 unknowns total between them. So I should be able to get all that into MathCAD and solve them simultaneously. So let's see, what's the best way to do that? Let's copy this. Can I get it all to match on one page? There we go. Copy that so I don't have to flip back and forth. Go to MathCAD, paste that in. Again, it's probably going to come in gigantic, so we'll scale it down a little. It went across the page. Oh, that's a little too small. Oh, that's kind of readable. Even that's readable. That's fine. All right, so we're going to do a solve block with these. So let's put solve block in. Remember, you have to have an initial guess for all of the variables in your solve block. So I have 6 different variables. We need an initial guess for all of them. So let's just do that. T, we're going to is 0. I don't think there's any reason to use units on this either. We'll leave the units off. FC is 0. AX is 0. AY is 0. And these can be any realistic number. The point of these initial guesses is to go in and, if there are multiple solutions, to be kind of close to the one that you think is correct. If, like for instance, there might be positive and negative solutions to a polynomial or something. If you give the initial guess closer to the one you're interested in, it's more likely that the solver is going to actually find that one instead of the other one that you're not interested in. So here, there should only be one solution for all of these, so I'm just putting in 0. That's all of them, right? 1, 2, 3, 4, 5, 6. So that's all of our initial guesses. Now our constraints are these equations. So why don't I move this over to the side so that I can actually see it at the same time. That might work a little better, huh? All right, so negative FC plus T times 6 over 7.81 plus regular T plus AX equals 0. This equal needs to be the control and equal sign. So that bold one, that's the symbolic equals. So it's not trying to evaluate it, and it's not trying to define it as something. It's just setting up it as a symbolic equation. T times 5 over 7.81. I did extra key there. Oh wait, that should be 5 though, right? Not 6. Get in there. Plus AY equals 0. Let's scroll down a little bit. We're gonna need more room. Negative FC times 48.3 inches minus AX times 10.5 inches equals 0. 160, since I didn't put pounds on any of these, I'm not going to put pounds on this one. So 160 plus FC minus T times 6 over 7.81 minus T. No, I don't want those parentheses that way. Do it that way. Minus T plus GX equals 0. Oh, not O, 0. Negative T times 5 over 7.81 plus GY equals 0. And minus GX times 58.8 plus T times 53.8 equals 0. So that should be all 6 of our constraints, which are the 6 equations we want to solve simultaneously. So we want to find, I want to find T, the problem statement is asking for the tension in the rope and the force on that pin at C. So I want to do those first. Find T and FC. In order for it to solve, I think I need to have all of them. So AX, AY, GX, GY equals. All right, we get some numbers. Now we have to decide if these numbers look real. So the tension in the rope came out to be positive. So that's usually a good thing because ropes can't support a compressive force. And I did draw them when I drew the tensile forces. I did draw them all in tension for the cable. So that looks good, and it's a realistic number. You know, it's 3. It's not like 2 million or 2 or something like that. So that's a realistic number. The force at C is also realistic. 93.9, also a positive number, which means that I drew this arrow correctly, and therefore I drew the other version of that arrow correctly. So that's we'll have to see how they want that put in, you know, because which do they want, the magnitude, or do they actually want a direction on it? I don't know. These others are the reactions at A and G. The negative sign here doesn't worry me. When I drew those, I just drew them randomly in the positive directions for X and Y. So it's totally possible that they're going in the opposite. In fact, if I look at the original thing, some reaction has to be going to the left because the external force is pushing everything to the right. So somewhere something has to be going to the left. So that seems fine. And the problem is not going to ask us for those anyway, so there's not a way to check that they've got the right sign, but let's put these in. So this one was 297, where'd it go? 297.662 pounds. And, oh, okay, denote a rightward force with a positive value. Well, that's fine, except do they mean the force on member ABC or the force on member CDEG? I don't know. Oh, here it goes. Find the force that body CDEG exerts on ABC. So, where's our pictures? That's this one. This is going the other way. It should be going to the left. And our problem said that a leftward force is a negative, so we need a negative in here. Negative, that can be really confusing. Most of the time on a test, I'm certainly not worried if a force is going left and right or up and down. I do worry if it's tension compression or the moments are clockwise, counterclockwise, but trying to figure out on a frame or machine, you know, which one are you talking about? Are you talking about the force on this piece or the reaction on that piece? It's not worth trying to figure that out. I'm looking at the magnitude there. This one wants a negative, and it's a negative 93.989, hopefully. And that would be pounds. I assume it won't, yeah. Be sure to include units. All right, so let's see. Gotta log in. Oh, we got them right. Good. Slight little bits of difference here. 662 and they have 673. I'm not sure where those differences might be coming in, honestly, because we solved everything in MathCAD. Oh, it could be that we rounded the 781 a little bit. It might be like 7808 or something. That's probably where the little bit of difference is at, because I just put 7.81. So that's, if there's rounding, that's probably where it's at. So that, like I said, is more than what you would do on a exam problem, because there's a lot of little pieces, a lot of little steps to this. But the idea of it, you know, maybe having to draw two free body diagrams and find what's common between them to solve. We kind of did that. I think maybe one of the problems in web work with the squirrels on a wire made you do something like that. Or maybe the triangle with the two wheels linked together might have had you do something like that. So that's not unheard of that something like this could be on the exam. This particular one's probably too much for an exam, just the amount of time you have on an exam. But that is how you would go about working that one. All right, let's look in the chat over here. Oh yeah, I forgot to put this poll up. Okay, things are okay, and I wouldn't be surprised that you need, again, there's only 4 people voting, but that's fine. Wouldn't be surprised that you need more practice with frames and machines. That's what this web work is for. And ask questions. We can work through most any of these, at least parts of them. This one we worked the whole thing, but we can work through them in the stream here. All right. The other thing we wanted to talk about is this idea of beams. So, I don't think we need MathCAD for beams. We'll get it out of the way. We will later, but not today. There it goes. So let's go over here and talk about beams a little bit. So, remember the general breakdown of the course. The first third is axial forces and stresses. The middle third that we're in right now is flexural stresses and forces that are not axial causing those flexural stresses. And then the last third is torsion and other things. So we are in the middle part talking about flexure. So things are bending now, or at least they can bend. And so I guess the simplest thing we could think of would be a beam, and it's got a pin at one end holding it up, and a roller at another end holding it up. This would be called a simply supported beam. So when you have a pin and a roller, it's a simply supported beam. If I go adding things to it or support it some other way, then it's not a simply supported beam anymore. The pin and roller don't have to be at the ends of the beam, although most of the time, or those problems we're going to work will have them that way, but that's going to be a simply supported beam. And it's going to have one of three types of loads on it, or some combination of these loads. Either one, it could have a whole bunch of loads on it, but you're going to have point loads, so that's what this guy is. You're going to have concentrated moments, and you're going to have some types of distributed loads. Sometimes we'll draw all these little arrows, sometimes we won't. Sometimes these will be evenly distributed, like this one, and other times they'll have some, random shape up here of their distribution. I guess it's not random, but something that's not even. All right, so that's kind of the setup that we will be dealing with. Another type of beam that we will also deal with is this kind. So over here we had a pin and a roller. Here we have a fixed support. This is called a cantilever beam. And the fixed support doesn't have to have it sticking out like a diving board. It could be at some random orientation here or something other than horizontal. Pretty much all the time, though, it's going to be horizontal for this course. And the fixed support has all three of those reactions. It has an X, a Y, and a moment at that point, where the pin and roller have two at the pin and one at the roller. If we ever have something that has some combination, like a fixed support and a roller, then that's over-constrained, meaning that we don't actually need the roller. We might in the real world, but as far as these equations go, we don't need the roller, and it's over-constrained. The methods that we're going to do in here can't really work with over-constrained problems. So we need statically determinant stuff. So that means three external reactions. We kind of ran into that, here. This one's technically over-constrained because it has four reactions over here at 2 at A and 2 at G. But we were able to work around it by, it's got a lot of common stuff, like this tension is on both free body diagrams, FC's on both of them. So we were able to work around that in that case. All right. Let's see. Let's talk about what we normally are thinking of when we're talking about beams is that these beams are flexing. So they're deflecting or bending. So let's set up a simply supported beam. Whoops. And look at that. So here's our beam. It's got a little point or pin and our roller. And let's just put 1 point load right in the middle of this thing. So we're not worried right now about the forces and the stresses, anything. Let's just think about it conceptually. So if this beam is small enough and this force is great enough, then the beam, let's say the beam originally had a center line kind of like this. Then if I push down hard enough, that center line is going to do something like this. So that is what we're calling deflection. It's probably not as dramatic as I drew there. You know, that's pretty severe amount of deflection. But we want to know when a beam does this, how far does it bend down? You know, how far does it deflect? We want to know that because it could be that this is part of a building or a bridge or some machine, and if these parts are deflecting too much, then that could be failure. You know, maybe it doesn't break in half, but it collides with something else, or it's just not aligned with something it was supposed to be aligned with. So that could be a failure mode that we need to be able to deal with, is this deflection. How rigid is the thing we built? Also, it could be that it deflects, you know, if it does like what I've drawn here, it's possible that I have deflected it to the point that it has yielded. Remember our stress strain curve? Let's just do that one real quick. So ductile materials or something like that with the stress strain. Remember, this is sigma, this is strain, so sigma is stress. And somewhere over here, I've got the yield point or the elastic strength. If I get so much stress in this beam, like as I load it up, let's say that it, you know, it follows this path, loading it, but I keep loading it, go past the yield strength, and I'm up here somewhere. I didn't get to the fracture point, so it didn't break, and then I remove the load. When it returns to zero stress, it doesn't go back down this graph that we drew. It goes back this way. And so this little path that I traveled on backwards, unloading, is parallel to this linear region when I loaded it. But now what happens is I've got some amount of strain built into the part. And so it's permanently changed its shape. It's permanently strained, which means it's changed its shape somehow. So what originally might have been a flat beam like I've drawn here, I overload it and deflect it downwards, and then I remove the load. It doesn't go all the way back to flat. It's got some amount of curve in it, and that's probably bad most of the time. So I want to know how much is that amount of deflection. I also want to know, do I exceed this yield strength? Like, as long as I stay below the yield strength when I'm loading it, then, you know, I'll load. And if I don't go past the yield strength, then when I return, I go right back to where I started from. So I'm only like stretching out atomic bonds. I'm not actually moving atoms around anywhere. And so I don't get a change in shape, a permanent change in shape. I might deflect it a little bit, but it snaps back to its original shape. So I need to know how much stress, you know, in this beam to make sure I'm not exceeding the yield strength. So that's a thing I want to know. These deflection stresses, there's internal bending stress, there's internal shear stress. There's two types of internal shear stress actually. All of that is internal. So I need to know, just like when I was doing the axial stuff and we would cut a little plate or a rod open and look at the forces inside it to see if they were tension or compression. We need to do the same thing here, except now the forces aren't quite the same as they were before. So let's look at, let's see, what do I want to draw next? I think I want to do this. So let's just say that I do bend this beam right here. So I bend it some amount, And let's zoom in on maybe a little piece of it right here. Just a little piece, but really zoomed in on that. So I'm going to, and it's bent. So that little piece looks something like this. So zoom in on that little narrow piece, and now it's like this. So if I look at that, then looking at the top of it, you know, right here, that's longer, or well, that's shorter than the bottom of it. Like I have stretched out the bottom and I've kind of compressed the top of it. So the top of this beam is in compression. And the bottom of this beam is in tension. So I have both compression and tension in the same beam on the same cross section. And so that kind of tells me a couple of things. For one, if I were to draw a stress profile, let's draw it right through the middle. So if I were to draw like how much stress is in this beam, I would say I'm going to draw to the left. I guess maybe that's left for you. That's compression. So that's my sigma max compressive stress. And over here, I'll draw this direction showing tension. That's my sigma max tensile stress. And between those 2 points, you know, it gradually gets less and less because I'm stretching it less and less. Over here, I am compressing it less and less. Somewhere in there, it's actually at 0. So this little dotted axis is the same as the original length. So the original unbent, unflexed length of the thing. So there's actually 0 stress here at this point in the middle. Now the middle is not necessarily the center. It is the centroid. The centroid of the cross section. So remember we did centroids a little bit at the end of last third of the course, right before exam 1. This is what we're going to, or this is one of the things we're going to use those centroids for, is figuring out where is this. This is called the neutral axis. So where in this beam cross section is the neutral axis? So that's the thing that we'll start doing also in practicing more with our centroids. But the neutral, meaning that there's no stress there. There's not compressive stress. There's not tensile stress. It's the transition point between compressive being negative numbers. So the top of this beam has negative 3,000 psi on it maybe. And the bottom of this beam has positive 3,000 psi. So if I went from negative 3,000 down to positive 3,000, somewhere on there I went through 0. And wherever I went through 0, that's this neutral axis. And the neutral axis is going to be at the centroid of the cross section. Okay. Let's see, what else do we want to talk about with this right now? Oh, these internal forces. So I cut this little bitty tiny piece out of the beam, and so now that I can see what's going on kind of on the ends of what I drew here, there must be some kind of forces there because I cut it away from the rest of the beam. So on this surface, this is a shear force. I'm just going to call it VR, which is the shear force on the right-hand side of the beam. So if there's a shear force on the right-hand side, you can imagine there's a shear force on the left-hand side also. They're not necessarily equal to each other, though. They can be different values. So this shear force is trying to like just shear the beam in half. So like if I've got, let's see, what can I do? I don't know, maybe like this. So I've got the beam out here, and this shear force is just trying to shear it, you know, just straight in half, like cut it with shears. There is another shear force in here. I don't have a good thing. Oh, maybe there. So like, this is a book. Let's get the cover off of it because that's going to not do what we want. So a book with a whole bunch of sheets of paper in it, if I bend those papers, then you can see how they're not lined up anymore. So there is a shear force between every sheet of paper. Every sheet of paper in there has a shear force between those layers. Same thing would happen. I mean, beams don't necessarily have layers in them. They sort of have layers of atoms in their crystalline structure. And those want to slide past one another whenever you bend it, just like the pages in a book would. So that's also a shear stress that is in these beams that are bending. We're not going to worry too much with that one. It's usually not a mode of failure. It can be, but it's usually not. It's more, I don't know, if you were maybe doing a laminated beam where you've got a piece of a wood or metal, and then you put it on top of another one, and there's this little tiny connection point between them, there might be some stress there that you're interested in, making sure that that doesn't come apart when it flexes. We're going to kind of not do that particular shear stress. What else do we have? We have the thing that's wanting it to bend. Neither one of these are actually making the beam bend. There's actually a bending moment. So I'm going to draw it this way. And I'll give it MR, which will be I'm going to call it the internal bending moment, and the R is on the right side. And then it's on the right side. So again, oops, left off the T. If I have a right side one, I also have a left side one. ML. These directions that I drew, with the moment on the right hand side being counterclockwise, moment on the left hand side being clockwise, shear force on the left being up, and shear force on the right being down. I don't want to make it look like that's the shear force. Those conventions are one of the few things where it does matter which way you draw the arrows, and it matters because of stuff we're going to do later. We're actually going to draw pictures of these shear force and bending moment anywhere in the beam. We're going to draw these pictures. And so for all of our pictures to be oriented the same way, we have to agree on what positive is and what negative is. And so this set of arrows, ML, MR, VL, VR, those are the agreed upon directions that are positive for if you're looking at the left-hand side of a beam or if you're looking at the right-hand side of a beam. All right, where are we at? Let's do a little more. Let's actually try to calculate these forces. Well, bending moments and force. The shear is a force. The M is a moment. So it's going to have units like inch pounds or Newton meters or something like that. All right, let's get us a clear page. And little beam. It's got a pin and a roller, so it's simply supported beam. And let's just put one 500-pound force on it. And let's say that this is 6 feet. And this will be 5 feet, just so it's not the same number. All right, so let's say that I have an interest in calculating the flexural stress in this beam at some particular point. So flexural stress, we haven't talked about that, but it's going to be sigma. It's not the same sigma that we had before, but this will be sigma. We're talking about flexural stress here. And the equation is the same idea, where it's still a intensity of forces, except now the forces are making things bend. So it's not just force over area. We're not going to derive this right now, but the equation we're going to use is sigma equals m times c over I. And technically it's a negative m, but that's not too big of a problem right now. And sometimes that c will be a y, but we'll worry with that later too. We don't know what I is yet. That's a new term that we haven't really talked about. So for now, let's use beams, like our little beam over here. Let's use beams that we can just look up a value for I. So let's say that this is a T-beam. So I'm going to draw a little, whoops, I didn't want an arrow on that. Just wanted this. So that's showing kind of the, the cross-section of this thing would be like this. So it's a T-beam. Or it might be a WT beam. W meaning wide flange T-beam. So if we can find information about a particular wide flanged T-beam, then we can just look up the value of I. So to do that, we need some charts. So let's go over here. Let's go to our introduction. Didn't actually go there. There we go. Reference materials. Here's, all right. This is, there's a similar chart, or actually this chart is in the back of your book. I am sure you can probably look up WT cross-sectional properties, and you can find that on Google. Your book has all these charts in it. The exam references have them in there. I'm just going to look at this one. All right. So this chart is, first of all, it's showing a T-shaped beam. There's the cross section. It's got all of these designations. These are the names of the beams on the far left, and then a whole bunch of data about different sizes and dimensions on the beams. Let's pick a relatively small one. This one looks good. WT4 by 29. So we're going to get all of this and put it over here. Let's get the heading too, so that we actually can see what these are all talking about. Oh, that didn't do what I wanted. All right, so let's arrange these the way they're supposed to be. Like that. All right. All right. So how these charts work is I've got, well, this is this top one, the one I just highlighted, that's a WT 4 by 29. All these underneath it are WT 4 by 20, 4 by 12, 4 by 9, 4 by 8. And so each one of these numbers in the names gives you a general, not exact necessarily, but a general idea of the size of the beam. So the letter WT means wide flanged T-beam. So the wide flange means that, let's see, like this part, I'm looking up here at the cross section I drew, that's the flange. I just colored it in blue. This green part, that's the stem. So flange on top, in this case, guess you could orient it some other way. Stem here. So the wide flange means that that flanges are wider than normal. So that's the WT. And so you have a whole bunch of these. You have W, you have S, you have C, there's a whole bunch of them. We'll gradually add to them as we get there. The 4 is the nominal, so not exact, nominal. They call it depth of the beam. I'm going to call it height. So it is nominal, so it's not an exact measurement. If you want the exact measurement, you have to look in the chart further. But what this means is that if our beam is a T with wide flanges, then it is approximately and the units for this particular chart are US customary units, so 4 inches. So it's approximately a little 4-inch tall beam. So it's not a very big beam. The 29 is pounds. In this case, again, I'm in US units, so pounds per foot. So if I took this little 4-inch tall I-beam, cut off a 4-foot section of it and weighed, or no, cut off a 1-foot section of it and weighed that section, it would weigh 29 pounds, more or less. So that kind of gives you an idea of how beefy the beam is. Because I've got others here, WT4, same 4-inch tall beam, but it only weighs 5 pounds per foot. So it's much thinner flange, much thinner stem, and so you can kind of get an idea of that. So that's how the names work. And then I've got all these dimensions over here. Don't worry with the axis XX, YY stuff yet, except that that's where we're going to get I. So I and I, there's actually 2 I's on this chart. For the time being, just know that we're going to use XX, the one under the XX column. So eventually, we'll talk about why you might want to use the YY. The short answer is that your beam is rotated from what it normally is, what the normal orientation is. But we're going to use this number for I. And until you learn any differently, just know that you're going to go, if you need the moment of inertia, oh, that's what I is called. Moment of inertia. Also known as the second moment of area. Remember, the first moment of area was the numerator in our centroid equation. So second moment of area, integral of y squared dA is moment of, and it's got units of inches to the 4th, so it's just going to be 9.12 is the denominator of our equation. C is, actually we need to go back a little bit to our picture here. So look at, there's that XX axis and there's the YY axis. We're dealing with the XX for the time being. Y sub C here, which you can see in the chart also, the values of it, that is the location of the centroid. So how far down, in this case, when we did centroids, we generally calculated from the bottom upwards. This one is calculated from the top of the beam down, and that's fine. But Y sub C is that distance from the top of the beam down to the centroid, where, remember, the centroid is the neutral axis location for the beam, which is an important location for beams. So C in our equation here is the largest distance. See, if I put y there, then it's not quite the largest, it's just some other number. We'll deal with that later. But the largest distance from the neutral axis, so NA is neutral axis, to either top of the beam or bottom of the beam. So in our case, looking at our little diagram over here, there's the neutral axis. Then the value of C, the largest distance, is going to be from that neutral axis down to the bottom of the stem. So that's what C is. Now that is not the number they gave us. They gave us the neutral axis to the top of the beam. So we'll have to figure out what the bottom length is, and we use these little numbers in here to do that. So let's draw a bigger picture of our beam so we can label some stuff. This is the cross section of our beam. All right. So according to our diagram, depth of T is 4.375. That is this distance. The beam's name was a WT4, so we knew it was around 4 inches. If we get down to it, a WT4 by 29 is actually 4.375 inches tall. But a WT4 by 20 is 4 1/8, so it's different. All right, so that's what that means. The flange thickness, this distance, 0.810 inches. So the little tiny WT by 5 is like 4 times thinner, looking at the flange thickness of it. The neutral axis is y sub c from the top, which is 0.874, this number right here. So I have to do some math to figure out what this distance is. Got to find my calculator. It is 4.375 minus 0.874. 3.501 inches. And that'll be the value C in sigma equals MC over I. In this case, because that 3.5 inches is the distance from the neutral axis to the bottom of the beam, and it's larger than the distance from the neutral axis to the top of the beam. I want the largest one because that's where the largest stress is going to be. The largest stress, tension or compression, is going to be at the top or the bottom of the beam. The smallest stress is going to be at the very center at the neutral axis where there's 0 flexural stress. And so I want that largest distance to figure out what the largest either tensile or compressive stress is going to be. So that's why I want C in there. I want the largest number. If I look at the equation, MC, C's in the numerator, so the bigger number I put in there, the larger sigma gets. The smaller number I put in for I, the larger sigma gets, so the smaller moment of inertia is going to create a higher stress. You can think about moment of inertia as how stiff the beam is compared to bending. Like how easy is it to bend. So a really big moment of inertia is hard to bend. Smaller moment of inertia is easy to bend. And M, again, the larger bending moment, which we haven't really talked about that much yet, but the larger bending moment is going to create a larger stress. So, but from here, we have a value for I is 9.12. We have a value for C is 3.501. We just need a value for M. So let's go back to our free body diagram. In fact, we might want to copy it and let's keep that guy too. Redraw it down here so that we can use it. Okay. When you have beams in bending, the bending stress, the flexural stress changes from one end of the beam to the other. You know, if I look at this little sample where I drew the dotted blue line, there's, more bending on one, there's more bending happening in the middle, less bending happening at the edges where it's supported. And so the bending stress is not consistent from one end to the other. So part of what I need to do is try to figure out, well, where do I want to know the bending stress? So I'm just going to pick a place right now. And that's why we want to draw these pictures I mentioned, is that's going to help us figure out where the worst case is. But for now, I'm just going to pick a spot. And I'm going to pick a spot 4 feet from the left end. So for whatever reason, I have decided that that's the spot in this beam that I want to calculate the bending stress. So we can write that down. So we're given this. Find flexural stress. Let's do maximum. Let's actually specify maximum flexural stress. On a cross section. Four feet to the right of the pin. All right, so that specifies that I want to find the maximum stress. That means I want to use C in this equation. MC over I, I want to use the C. It also says where, 4 feet to the right of the pin. And now I just need to figure out what M is there. So how you do this is, I kind of already led into it here by drawing my little green squiggly line. I'm going to draw a free body diagram of that piece of the beam. Before I do that, I need to find the reactions though. So I need to find the reactions at the pin and the reactions at the roller. So let's see if I can. Oops. There we go. Line it up a little bit. At the pin, I would have. I know I drew these kind of indented a little bit. Actually, that's fine. We'll just line it up with that. So the pin, I'll call that point A. So I'll give it an AY, and we'll put AX over here, and then this we'll call B, and we'll give it a BY. It's a roller, so it doesn't have any resistance to rolling in the X direction. It only resists moving in the Y direction. I can already look at it and see that, well, AX is 0 because it's the only force in the X direction, so it has to be 0. So let's write summation of moments about point A equals 0. And that will say I've got 500 pounds. It has a 6-foot moment arm going clockwise around point A. Point A is roughly right in there somewhere. Minus counterclockwise BY times 11 feet. Therefore, AY, BY, not AY. AY is not in that equation. Therefore, BY equals, and let's see what it equals. So 500 times 6 divided by 11. 272.73 pounds. And then I can do summation of forces in the Y direction equals 0, and I have AY plus BY minus 500 pounds equals 0. Therefore, AY equals 500 minus 272, which is 227.27. So I've got my two reactions. Okay. I didn't actually need both of these reactions, but I just did them both. All right. Now, let's draw a little free body diagram. I'll draw it a little bit larger just because we're going to have to draw some labels on it and such. But there is the little left-hand side, and it's, it's a T-beam, so you could kind of see the edge of the flange there, I guess. When we draw this side, we have to put our arrows. The shear force goes down, and the concentrated moment, the internal bending moment, goes counterclockwise. So shear force goes down, V. Bending moment goes counterclockwise. AY goes whatever way AY goes. AY, I drew it upwards, it came out positive, so it must go up 227.27 pounds. and then I know that I cut this thing at 4 feet. So I can, this is a free body diagram, so I can write 3 different equilibrium equations for this diagram. The X one doesn't do me any good, so really only 2. I can write, for this diagram, let me move it down so it doesn't look like it's colliding with that one. So for this free body diagram, I can write summation of forces in the y direction equals 0, and I get 227.27 pounds minus V equals 0, so therefore V is also 227.27 pounds. The bending moment M doesn't have an X or Y component. Then I can write summation of moments. I'm going to write the summation of moments about my little wavy cut line. And I'm doing that, I'm going to do clockwise positive. I'm doing that because the shear force won't be in that equation. Not that it matters, I could put it in there, but it's just simpler to not have it to write down. So clockwise positive, the way I drew it, you're going to see a lot of these counterclockwise positive because the way that we assign these, a lot of times you're dealing with this one and it is counterclockwise, and so a lot of people want that to be positive, and that's fine. I just, for whatever reason, I typically do clockwise positive when I'm writing the moment equations. All right. But you will see a lot of counterclockwise positive, and it's fine. So what I've drawn here, if clockwise is positive, then, and I'm doing the moments kind of about this point right here, that's where I'm calling my cut point, then I've got 227.27 pounds. It has a moment arm of 4 feet. The way I had to draw M here is counterclockwise, so that's minus M. Concentrated moments do not have moment arms. They already have feet and inches and meters built into the units, so you don't need to multiply by it again, or you'd have foot squared pounds, which is not a moment. So just minus M equals 0. So therefore, the bending moment at this particular spot in the beam equals 227.27 times 4. 909 point, I'm just going to call it 0.1. It's 0.08. I'm going to call it 0.1 foot-pounds. So now we know M. We already had found C, and we had already found I. So I can calculate sigma max at this section equals negative M times C over I. So the negative is part of the equation. So negative 909.1 foot-pounds. I'm going to convert those to inch-pounds, so times 12 inches per foot to get into inch-pounds, times C, which we found earlier on, it was right here, 3.501 inches. And remember, this C is the largest distance from the neutral axis to one edge, top or bottom, of the beam. And I want that because my problem statement said to find the maximum flexural stress. So I need the maximum number for C that I can put in the equation. All right, so we got that. And I is, I guess I never wrote it down, but we said it. This is a WT 4 by, I think it was 29. Already forgotten. Yeah, WT 4 by 29 beam. And so the I, moment of inertia for that particular beam, is 9.12 inches to the fourth. So when I work these units out, the feet cancel out. I have inches squared pounds in the numerator, inches to the fourth in the denominator. So I'll have pounds per square inch, which is a PSI. And the number, and it's negative. Oh, no, it's not negative. Hold on. This 3.05, we got to be careful with that. So neutral axis of our cross section, that is the reference now. We're measuring from the neutral axis. So when I measure from the neutral axis down to the bottom to get C, that's the negative Y direction. So this is actually negative 3.501. So that negative times the negative that's built into the equation actually makes this number positive. And that positive means tension. So it's a tensile stress, which we already knew. You know, when our beam bends downward, the bottom gets longer and it's in tension. So we already knew that, but now our equation actually says that. So now we've got 909.080 times 12 to convert to inch pounds times negative 3.501 divided by 9.12. So I think I get 4,187.75 units of pound per inch squared. So that's 4,187 point, I'm just going to do 8 psi, or 4.2, we'll get even more rounded, ksi. So I can take that number and then I can go look up material properties to see, is that number dangerous for yield strength for this material. Most of these beams are going to be steel, and their yield strength is going to be something like, what is it, 36 ksi, so 36,000 psi. We're at 4,000 psi, so we shouldn't, for most materials that these beams would be made of, be anywhere near yielding it. So on our little graph right here, you know, we're doing something like loading it up to maybe right here, maybe something like that, maybe not even that far. Whoops. If this number up here is 36, though, we're like way down in here somewhere. So we're nowhere near yielding it. All right, I think that's probably a decent spot to stop. It kind of gives you an overview of all the things. And the next thing we'll do is just repeat some of this stuff, and this is tomorrow. And we will start the process of, all right, well, where is the maximum bending stress in this beam? And so that's going to lead us down a couple of roads, one of them which will be shear and bending diagrams, pictures of the shear force and bending moment anywhere in the beam. So that's where we're headed. All right, I will see y'all tomorrow, same time, and let me know if you end up with some questions, you want a web work problem or something worked before we head off into beams. There are, I believe, I'll have to check and see. I might not have put the web work problems for the beams up yet. That might still be the frames and machines problems. I'll look and see. All right, I will see y'all tomorrow.